All right, we're moving on to the next section, which is talking about rational functions. Now, these guys are going to be a little bit trickier to graph, but just like the other functions that we've talked about, we're going to discuss the key points, we're going to talk about domain and range, and we're going to talk about how the shifting and the graphing transformations that we did for the parent functions a long time ago are still going to apply to these new pictures. In fact, we're just adding shapes to what we've already seen. So here's what we know about rational functions. Okay, so a rational function is anything that's of this form. F of x is equal to p of x divided by q of x. So when we talk about the word rational, we're talking about ratios, we're talking about fractions, and so that's what we're talking about here. We're talking about a function that is a fraction. It's a quotient of two other functions, okay, where both p of x and q of x are polynomial functions. So these guys are polynomial functions. It's just the quotient of two polynomials. And the denominator does not equal 0. It's not the zero polynomial. Because if q of x is the polynomial that's always 0, then you're always dividing by 0, which means you're going to have a function that's not even defined, so we can't even talk about it. Now, we will bring up the concept of restricted values that we talked about at the very beginning of the semester. That's still going to come into play here. So as you think about the main functions that we've talked about, we've said that for almost everything, the domain is going to be all real numbers, unless we run into one of two situations. One, if we have square roots, we've already seen how in a square root, the expression has to be non-negative. And so that creates a restriction for us on our domain. The other concept that we can see that can restrict our domain will be that of fractions, like what we're seeing here. So with fractions, almost everything is permissible, except you can't have your denominator equal 0. If your denominator is equal to 0, that's bad news. You're dividing by 0, which means you're undefined. So for a function that is a fraction, the domain will be all real numbers except for those values that make the denominator 0. Now, there are two main functions that we're going to talk about. Okay, so the first guy is what we call your reciprocal function. Okay, so let's talk about him, his basic shape, and then we'll talk about the other function here. So your reciprocal function does exactly what the name suggests. Whatever you plug into the function, you get the reciprocal. And it looks like this. It looks like 1 over x. So when we think about what our key values are for this, we're going to plug in -2, -1, -1/2, and then we're going to go to 0, 1/2, 1, and 2. Keep in mind that we're talking about doing the reciprocal. So the reciprocal means take your fraction and turn it upside down. So the reciprocal of -2 is -1/2. If you flip -1 upside down, you get -1. If you do the reciprocal of -1/2, that's -2. 0 is where we have problems, because if I try to plug in 0 here, 1 over 0 gives me something that is undefined. We're going to see how that will affect us when we talk about the domain. Okay, the reciprocal of 1/2 is 2, the reciprocal of 1 is 1, and the reciprocal of 2 is 1/2. Now, if these values keep getting bigger and bigger, my fraction is going to be a value that's smaller and smaller. So if I were to go out here and I do 10, well, the reciprocal of 10 is 1/10. So that denominator is getting bigger, which means my value is getting smaller. In fact, I keep plugging in larger and larger numbers. This output is going to get smaller and smaller and smaller. It's going to try to get to 0, but it never will. So these are the key points that we have. I mean, don't need to worry about 10 because he's not going to fit on here. But these other ones are the key points that we have that we're going to plot. So before I plot these guys, well, no, let's plot the points, and then we're going to see some weird stuff happen. Okay, so -2 gives me -1/2, so it's about right here. -1 is -1, and then -1/2 is going to be down 2 units like that. And then I've got this little jump over here, so 1/2 gives me 2, so here's 1/2, gives me 2, 1 gives me 1, 2 gives me 1/2. If I keep on going out towards the right, excuse me. If I plug in 3, I'd get 1/3. I plug in 4, I get 1/4. And these numbers are going to get smaller and smaller. They're going to get closer and closer to 0. However, they are never going to actually hit that x-axis. So when we graph this, you're going to see that as I get closer to the y-axis, I'm never going to cross it. I'm just going to get very, very steep. And as I go to the right, I'm going to get closer and closer to the x-axis, but I don't include that. I'm never going to touch that. And you might say, well, it looks like you're touching it here. I'm doing my best, not to touch it, because it doesn't. They never, ever touch. And then you have a shape that's very similar here on the left side. So he's also going to skirt right up against that y-axis, and then underneath, he's getting closer and closer to the x-axis like that. So some of the things that it's kind of hard to see here are what's going on as you go out towards the left and the right. So the further I go out here to the right, this guy gets smaller and smaller, and he starts to get closer and closer to 0. On the left side, that guy's coming from underneath, and so he's going to get closer and closer and closer to the x-axis from underneath, but he's never going to touch it. And so when we talked about polynomial functions, we talked about in behavior. We talked about whether they were both going up or in opposite directions and all that stuff. For these rational functions, their in behavior, for most of them, is they just kind of flatten out, and they start to get closer and closer to this x-axis. Now what we have here is something called a horizontal asymptote. Now, horizontal asymptotes can be crossed. You can cross over a horizontal asymptote. It doesn't really matter if you cross it. What matters is how it describes your in behavior for this function. So this horizontal asymptote for your main parent function here for the reciprocal function is y equals 0. And what we're saying here is not what's going on in the middle of the function, but as you go out towards the edges, you start to approach 0. Now there's this other asymptote that we have right here. So you see how we're getting closer and closer to the y-axis, but we never actually touch that. So just as you have a horizontal asymptote, we have a vertical asymptote. And for this example, and for a lot of these key functions, these parent functions, that's going to be x equals 0. And so you see that as I get closer and closer to it from the left side, I can't cross that. The closer I get to 0, and I start doing those reciprocals, the bigger the number is. So when you divide by a smaller and smaller number, your result is bigger and bigger. However, if you divide by a bigger number, like we see right here, then the result is smaller. And so one of the ways we kind of describe this shape is, my students in the past have talked about it as being the missed high five. So you're going, and you just kind of miss. That's what's going on. These guys are never going to touch because you have this guy right here, this vertical asymptote. Now, I said you can cross horizontal asymptotes, but you can never cross a vertical asymptote, because a vertical asymptote is showing up whenever you have something that's undefined, when your fraction is undefined. Now, I'm not saying that every time it's undefined you get a vertical asymptote, because there's some weird things like holes, but we're not going to get into that this semester. So let's talk about what the domain and the range is for this. So if you look at this picture, your domain is almost all real numbers. It's everything except for this x value of 0. So that's going to be from negative infinity to 0, parentheses, and then union from 0 to infinity. And all you have to do is look at this original expression. You can plug in any value that you want to for x, except anything that makes that denominator equal to 0. So what makes x equal to 0? Well, 0, naturally. Now, that's the domain, and if we want to identify your range, remember your range is going from bottom to the top. This guy goes all the way down to the bottom, he goes up, and he gets as close as he wants to that y value of 0, but he never ever gets to touch it. So he's going to be going from negative infinity to 0, union 0 to infinity. So that's what your domain looks like, and that's what your range looks like. Now, I know some of the questions that you're going to run into when you get into the MyMathHub homework, and they're going to ask you questions about, just like we've had in the past, where are you increasing and where are you decreasing? Now this one gets a little bit tricky. So here's what you need to look at. Where are we increasing? Now remember, increasing is as you move from left to right, where are you going up? As I go from left to right, I'm getting lower and lower and lower. And then there's a break. There's this disconnect where we have that vertical asymptote, and we are decreasing still on that. So if the question is, where is this function increasing? We can say, well, he's not increasing. This guy is decreasing for each of the different sections that we have. So he's increasing nowhere. But where is he decreasing? Well, if he's not increasing, he's going to be decreasing. But you've got to make sure that you describe this the right way. Because I know this question, and I know that students think they've got it right, and they go, how did I get it wrong? Okay, so where are you decreasing? Well, you see here as you trace, you are decreasing for this section, and you're decreasing on that section. But the way that you have to write this answer in MyMathLab is like this. You are decreasing on this interval from negative infinity to 0, and then comma, because you have another section where you are decreasing, you're decreasing from 0 to infinity, like that. So what you have to understand is that when you're typing this in MyMathLab, this is going to be the box that you type in. You don't use a union sign, okay? Now I know that for our domain, we said our domain is negative infinity to 0, union 0 to infinity. Because when we talk about unions, or so when we talk about domain, we talk about range. If there's a break, we use the union sign to connect that. When the question is asking where you're decreasing, what you're basically giving are answers. You are decreasing here. You are also decreasing here. But since they are disconnected, you can't use a union. You're saying it's decreasing for this section, it's decreasing for that section, but you don't join them. So make sure that you're very careful whenever you are typing your answers in to MyMathLab. All right, so we have one more function to look at, and that is going to be the reciprocal squaring function. All right, so we're going to do the same stuff that we just did, now for the reciprocal squaring function. And so once we have this shape, it's just going to be a matter of taking all of the graphing techniques that we've talked about this semester and applying it to these shapes and just moving them around. Your reciprocal squaring function looks like this. 1 over x squared. So just like the last guy would do the reciprocal, he's also going to do the reciprocal, and then he's going to square that result. So let's look at those key values in a t-table. And let's use the same values that we were using above. All right, so we're going to do -2, -1, -1/2, 0, 1/2, 1, and 2. So you've got two ways of doing this. You have to flip and you have to square, but the order doesn't really matter. So if you want to take negative 2 and square that first to get 4, that's fine. And then do the reciprocal of 4. So you would end up with 1/4, positive 1/4. Watch out for those signs. Negative 1. If we square that, it's positive 1. And the reciprocal is still 1. Negative 1/2. This might be one of those numbers where I want to do the reciprocal first and then square. So the reciprocal of negative 1/2 is negative 2, and negative 2 squared is positive 4. Cool. 0, just like we had in the reciprocal function, is not going to work here. And it's going to lead us to something that is undefined. You plug in 0, 0 squared is 0, 1 divided by 0 is undefined. You're going to notice that these output values on the other side are going to mirror what you see here. When I plug in 1/2, I'm going to get 4, then I get 1, and I get 1/4. Alright, so let's plot these points and see what we have. So negative 2 is a positive 1/4, negative 1 is positive 1, negative 1/2 is positive 4, like that. And then we see the symmetry on the other side. 1/2 is 4, 1 is 1, and 2 gives me 1/4. As the numbers get larger and larger right here, if I plug in 3, I'm going to get 1/9, 1/16, 1/25, and so on. It's going to get smaller and smaller and smaller and smaller, but it's never ever going to equal 0, which tells us that just like in the last problem, we are going to have a horizontal asymptote right here. Also, since we're undefined when x equals 0, we're going to have a vertical asymptote right here going through the middle. Now, the neat thing about these asymptotes is that when we start doing the shifting of our graphs, those guys will act as our new x and y axes, just like we had to graph them before. We need to graph our asymptotes anyway, so it's kind of convenient that when we slide these guys around, that's going to be your new x and your new y axis, so it's really easy to graph from there. Now your shape. So I'm just going to start connecting these and do the curve as it goes up, and he's going to get really, really steep and look something kind of like that. And he's going to get really, really flat over there. And you have the same shape here on the right side. Keep in mind what your graphs are supposed to look like for these reciprocal and reciprocal squaring functions. Okay, so the one that we had above, you're coming from the left and you're just curving down, and you get this other part right here. This piece right here never curves back over. If it were to curve back over, it would fail the vertical line test and it wouldn't be a function, so be very careful how you do that. Also, please note that it's never going to go completely vertical. It never does that. When I look at the graph down here, it's really flat and then it gets really, really steep. These guys never meet though. They never ever meet because you have this single value that causes your expression to be undefined. Now, the name that we have for this guy is a volcano. Kind of looks like a volcano to me. He's just going like that. Alright, so what is the domain? Let's see. It looks like my domain should be the same as the reciprocal function. So my domain is going to be all real numbers except for 0. So negative infinity to 0, union 0 to infinity. And then my range. So the range is going to be a little bit different because it doesn't go all the way down. He doesn't start until you get right here with a y value of 0, and then he just goes up. So that's going to be from 0 to infinity. And since we have this horizontal asymptote, we know that this guy's never going to equal 0. So he's going to have parentheses on that. And now let's finish this by talking about where is this graph increasing, where is he decreasing? Is he increasing anywhere? Well, let's see. As I go from left to right, I'm really kind of flat right here, but he is increasing. And then over here, he's going down as I move my finger from left to right. So he's increasing on the left half. So he's increasing from negative infinity to 0. And then he is decreasing, starting just beyond 0 and going out to the right toward infinity. Okay? So these are the two basic shapes, and now what we're going to do in the next couple of videos is we're just going to take these shapes and just move them around, shift them, apply transformations to them, maybe even do some reflections, just like we've done in the past. So stick around.